This next question is similar to the previous one. We are asked about the number of positive divisors of at least one of the numbers, or one of the exponentiation here at the bottom: 10 to the power of 60, 20 to the power of 50, and 30 to the power of 40. Yes, they look very large, but we have a strategy in solving for this because we are given with the principle of inclusion and exclusion. We just simply need to take out, if we talk about at least one of the numbers, we are going to take the cardinality of their unions. Let's say, okay, let A be the set of positive divisors of 10 to the power of 60. Let B be the set of positive divisors, pardon if I'm going to do it like this one, 20 to the power of 50, and C be the set of positive divisors of 30 to the power of 40. And with that, we can actually solve for the result using this formula: cardinality of A plus the cardinality of B plus cardinality of C minus the cardinality of the intersection of A and B. Why do we subtract this? Okay, I'm going to explain it later on. Of course, this was already explained previously together with this and the intersection of that, and also at the same time the addition of the intersections of all three. Now, this is the idea of the principle of inclusion and exclusion. First, why do we subtract this one here? In short, the intersection of A and B. That is because when we count the number of positive divisors for 10 to the power of 60 separately with 20 to the power of 50, a number of them were counted twice. One of the example is 2. That's very simple example. 2 is a positive divisor of 10 to the power of 60 because 10 is, by the base itself, that's divisible by 2, and whichever its exponent, it will always be divisible by 2. At the same time, 2 is also is a positive divisor for 20 to the power of 30 because then again, 20 divides 2. Or 2 divides 20 rather. So 2 was counted twice. That's why we are going to subtract that here. Similarly, 2 is also here, right? 2 is also between 10 and 30. So that's why we have exclusion, the principle of inclusion and what to be excluded. And the reason why we are adding them here, that is because 2, as mentioned, 2 was counted twice here. So we subtract that, another here and here. So we are going to add the counting because once we remove 2 3 times or multiple of times, it will also be a part of the intersection. So we're going to return that so that we will actually be, so for example, let's say for example, 2 is here, right? 2 is also here, 2 is also there because 2 divides 20, 10, and 30 of the bases. 2 is here, as mentioned earlier, 2 is here, so 2 is there. Once you remove all of them, that's 0. But 2 should be part of the union. That's why we return 2. That's this explanation. Hopefully that's very clear now that we are also adding that. That's also discussed previously. The only problem that we can see here is how do we identify the number of positive divisors per exponentiation? Because that's very large. This is how we do it. We actually have a formula in finding the positive divisors of any exponentiation. So for example, for any exponentiation here, let's say, how do we identify this? Say for example, x to the power of any exponentiation, right? Just like that one. Say for example, that is exponentiation. Using prime factorization, if we could find prime factors for this, might be more than 2 prime factors with an exponent here, let's say k, and then we have here m, or let's I'm going to redo this one. Let's say this is k, this is m, this is n. You'll be guided. X to the power of k, m, and n. If we could look for the prime factors of said exponentiation having m and n exponents, the number of divisors, positive divisors, actually computed as m plus 1 times n plus 1. If there are 3 of them, let's say another p to the power, p of sub 3 power of, let's say, r, so you still multiply this with r plus 1. That's actually one of the items in the number theory that we have learned before in finding the number of positive divisors. So we are going to do this for all of these three to find the positive divisors for each. Now it would correspond to the result here. As for the intersections, we'll attack it later on, so let's do it step by step. Let's start with 10 to the power of, as mentioned, 10 to the power of 60. Now it's very large, but we can of course factor the base itself as 2 times 5 to the power of 60. That those are already prime factors. Now, if you're going to use the power law, you will have your 2 to the power of 60 times 5 to the power of 60. And since they are already prime factors, using that, you will have, using this formula here at the bottom, you will actually have the cardinality of your A is actually 60 plus 1 times 60 plus 1. Take note that the number of elements or the cardinality for each set depends on what type of set it would be. Previously, we had set S having integers 1 to 1000. Simply count the number of integers. We might also have, say for example, set S containing number of cards in the deck, so we know how many cards are there. But this time, positive divisors, so we need to really identify what type of sets do we have, so that we can actually get the correct answer. 61 times 61, you will get here the number of positive divisors. For 10 to the power of 60, you will get here a result for your cardinality of A being 3721. So first item is already okay. Now for the next, you will have 20 to the power of 50. Let me write it at the bottom because this might need a lot of steps. So 20 to the power of 50. So by prime factorization, that's 4 times 5 or 2 times 2 times 5, because you can need to factor them in its prime form, so that we can use this formula here as indicated in our number theory. So that's power of 50. By power law, you will have here 2 to the power of 50, 2 to the power of 50, 2 to the power of 50, 5 to the power of 50, which gives us 2 to the power of 100 using multiplication law of exponents. So you will have that. Okay, same base. So the cardinality of B is actually 100 plus 1 times 50 plus 1, which is actually 101 times 51. Using your calculators, you will get there a result of the cardinality of B is equal to 5151. Right? Now, next, let's proceed to C. Cardinality of C is the prime factors, or 30 to the power of 40. Again, by prime factorization, how do we get the prime factors of 30? 6 times 5 will do, and 6 is actually 2 times 3 times 5. Right? So by, again, power law, 2 to the power of 40, 3 to the power of 40, 5 to the power of 40. We have 3 of them, similar to this example. So you have 40. The cardinality of C is 40 plus 1 times 40 plus 1 times another 40 plus 1, because there are 3 prime factors there. So 41 times 41 times 41. The cardinality of C is 41 cubed. That's actually 68,921 positive divisors for 30 to the power of 40. Now, okay, so we're done with all of this. We might need a lot of space later on, so please bear with me. I'm going to move to another page, because the next item would be the cardinality for intersection B. So how do we identify the cardinality of A intersection B? We don't need this anymore. We don't need we might need the prime factorization, but we don't actually need to use the power law, etc. Here's the hint, and this is also discussed in the previous video. For this, take note that A talks about the 10 to the power of 60, and B talks about 20 to the power of 50. To get the cardinality of the intersection, we simply need to get the GCF, okay, of 10 to the power of 60 and 20 to the power of 50. Why do we need to get the GCF of both? The idea there is, when we talk about the greatest common factor, that given exponentiation later on corresponds to the number of positive divisors in the intersection. Hence, we still need to use the same formula later on to get the result. So, the GCF here, we know that in exponentiation, that's GCF. The exponentiation of 10 to the power of 60 is 2 to the power of 100. 100 times 5 to the power of 50. It's here, this one. And then for B is, that's B, my bad. That is for B actually. For our A was 2 to the power of 60, 5 to the power of 60. Okay. 2 to the power of 60, 5 to the power of 60, then 2 to the power of 100, and 5 to the power of 50 for our B. So the greatest common factor for that is the least number of exponents. So you have 2 to the power of 60 for 2, and 5 to the power of 50 for our 5. this stands for the exponentiation for our intersection of A and B. So for our cardinality, this is not necessarily equal for the cardinality, okay? So I'm going to remove the equality here. Okay? So you will have A intersection B is same formula, 60 plus 1, plus 1 times 50 plus 1. You will actually get here 61 times 51. So 61 times 51, you will get 3,111 for the intersection of A and B. Right? Now, for the intersection of A and C, it's the GCF of 10 to the power of 60 and 30 to the power of 40. Now, this is actually the GCF of the exponentiation 2 to the power of 60, 5 to the power of 60, and then for our 30 to the power of 60 is here. There are 3 factors, 2 to the power of 40, 3 to the power of 40, 5 to the power of 40. So there are 3 of them. Take note, we're talking about the greatest common. What's found in both. 3 is here, but 3 is not on the other one. So the greatest common factor is just 2 to the power of 40 and 5 to the power of 40. We don't include the 3 because it's not common in both. So our cardinality for A intersection C is actually 40 plus 1 times 40 plus 1. So you will have 41 times 41. You will get here our result using your calculators, 1,600. Sorry, that's a comma. 1,681. Okay, so we are done with this 2. We still have 2 more. That's why I may be using another page here. Okay, so I will add another page. So this time we are on the cardinality of B intersection C, and this corresponds to the GCF. Sorry, that's GCF of our B is actually 20 to the power of 50 and 30 to the power of 40 as previously indicated here, right? And this is actually equal to the GCF of your 20 to the power of 50 is actually 3, right? Yeah, 3 of them, 22, 3, and 5 raised to the power of 40. So you have 2 to the power of 40, 3 to the power of 40, 5 to the power of 40, and then for 30 to the power of 40 is that's 30 to the power of 40. This is actually my bad. So I'm 2 to the power of 100 and 5 to the power of 50. My bad. Okay? So I'm going to erase this. 2 to the power of 100, 5 to the power of 50, and then here 2 to the power of 40, 3 to the power of 40, and 5 to the power of 40. Okay? So GCF again is the common between them. So 3 is here, but it's not on the others. We will not include that. So 2 to the power of 40, the minimum exponent, and 5 to the power of 40. So the cardinality of B intersection C is 40 plus 1 times 40 plus 1. That's 41 times 41. You will get the result of 1,681. So we're almost there. The last one is actually the intersection of all 3. So this is very long because our item is also very complicated to look at. It's exponentiation. But by the use of a principle of inclusion and exclusion, it will be solvable. For this time, we'll be using the GCF of all 10 to the power of 60, 20 to the power of 50, 30 to the power of 40. Okay? So again, it's not equal. Okay? We will solve for GCF first. So the GCF of this again? 2 to the power of 60. Okay. 2 to the power of 6. Again, my bad. I used to writing 0 after that. 5 to the power of 60. If I'm correct, this is 2 to the power of 100, 5 to the power of 50. This is 2 to the power of 40, 3 to the power of 40, and 5 to the power of 40. So the common for all, the minimum exponent we have here, 2 to the power of 40. For our 5 is also 5 to the power of 40. We don't need 3, again, because we're talking about the common. Similarly, we have the same result here. So if you would like to, the cardinality of A intersection B intersection C is 40 plus 1 times 40 plus 1. We'll get 41 times 41, which will result to 1,681 as well. So all of them are now given. So let's try to solve now the intended result for the number of positive divisors of at least one of 10 to the power of 60 to 20 to the power of 50 and 30 to the power of 40 is the union of A, B, and C, which is the cardinality of A plus cardinality of B plus cardinality of C less the intersections of pairs and add the intersection of all, because again, as mentioned earlier, some of this already removed. So the cardinality of A, cardinality of A is this 3,721. 3,721 plus cardinality of B, it's here, right? 5,151. 5,151 plus cardinality of C, 68,921. 68,921 minus intersection of A and B, 3,111. 3,111 minus intersection of A and C, 1,681. 1,681 minus, we have it here, the intersection of B and C, still 1,681 plus the last one, 1,681. So add all of them. This results to our target. Let's do it step by step. 3,721 plus 5,151 plus 68,921 minus 3,111 minus 1,681 minus 1,681 plus 1,681. This is equal to 73,001. This is the total number of positive divisors for at least one of the exponentiations already identified. The answer is 72,001. So this is the result here, 73,001 positive divisors for at least. It would mean some of them are only for 10 to the power of 60, some of them are 20 to the power of 50, some of them are on 30 to the power of 40 or in the intersections, or even some of them are for the three of the exponentiations, considering all the multiples already removed. So this is how we solve this kind of item. Again, the number of elements or cardinality of your set depends on what type of sets you have. So please try to look into the type of sets, and then later on look into connections, because we connected the type of sets here on our number theory concern on finding the number of positive and divisors. Thank you very much for watching.